All right, we're moving on to section 4.4 today. It's called modeling and optimization, but before we get there, here's a nice warm-up that you can use. So pause the video, and when you come back, I'll actually go through, well, I'll just show you the work here. You can see right here, we're trying to use the first derivative test to find any local extrema. So you take the first derivative, set equal to 0 to find your critical points, and then analyze the first derivative to the left and to the right of that critical point. You can see in this problem, we really only have one critical point. The only critical point is 2. To the left of 2, we have a positive first derivative, and to the right of 2, we have a positive first derivative. Since the first derivative does not change signs at the critical point is not an extreme value. There are no extrema in this problem. Versus the one that we have for the second derivative, you can see finding the first derivative and setting equal to 0 in order to find our critical points. Once we find our critical points, analyzing the second derivative at those critical points. So we can see our first critical point of -2. We evaluate the second derivative at -2, and we find the second derivative is negative. Second derivative being negative means we have concave down. So again, last section, I told you that I always draw this in the air to see whether it's a max or a min. So I can see concave down is going to have a maximum on it, which is why -219 is a maximum on this function. Local maximum, not absolute maximum. Next, we find our other critical point at 0. Our second derivative is positive at 0. So positive means concave up. And when we draw the concave up, we can see that the concave up would have a minimum on it. And the last one was actually supposed to be the easiest one, especially since you all have Google machines right in front of you. You can just Google the volume formula for a cone, but it is 1/3 pi r squared times the height. So 1/3 times pi times 4 centimeters squared times 7 centimeters would give you 112/3 pi centimeters cubed, or about 117.286 cubic centimeters. Now, I would imagine at this point in knowing me, you know that I like exact answers, so that 112/3 pi cubic centimeters really pleases me more. But when we have real-world applications, you don't want to please me. You want to please the customer, whoever's paying you to do the work. And if you have somebody paying you to do math work, it means they don't want to do the math work themselves, and they probably want an answer that they can visualize. So in real world application problems, you probably want to give a decimal answer, even though I don't like them. Right? Now, on to section 4.4, modeling and optimization. It helps to understand what we mean by modeling and optimization. Modeling means creating some sort of mathematical formula to represent a situation that is happening. Optimization means getting the best result from whatever situation you're talking about. Sometimes an optimized value is going to be the biggest value. Like, for example, if I want to build a pen for a dog, I want to maximize the area of that pen so the dog has the most space to run around. But in that pen, I also want to minimize the amount of fencing that I use around that pen, because fencing is expensive and I don't want to pay for more fencing than I need. So in your book, there are some steps. They're on page 219. Those are the steps that Finney, Damana, Waits, and Kennedy thought would be good for solving an optimization problem. I like these steps a lot better. They just work better for analyzing these types of problems. And those of you who are in physics probably recognize them as pretty similar to what Mr. Harvey uses for you. But those steps, you might want to write them down, are 1, read and understand the problem. Always read the problem before you start to do it. 2, draw and label your picture. 3, assign variables to the quantity that you want to optimize. 4, write some sort of equation that results in the quantity that you're trying to optimize. And 5, get that equation into one variable, because we are talking about single variable calculus, not multivariable calculus. And then step 6 is really the only calculus that we do here. You find the max or the min and answer the darned question. All right? All right, so you guys can actually see that this is problem number 3 on page 226 in your book. And we want to find the smallest perimeter possible for a rectangle whose area is 16 square inches. And what are those dimensions? So a couple things that I have here. When I try to understand a question, I really like to highlight stuff that's important. So what I see here, I see smallest perimeter. Smallest perimeter means I am trying to optimize the perimeter. Eventually, I'm going to set up an equation for perimeter and find the minimum value for that perimeter. Some other stuff that I see here, I've got the area is 16 square inches. And ultimately, we're going to try to figure out what the dimensions are here. And it's important to know that we're talking about a rectangle. All right? So now, step 2. Draw and label the picture. All right, this picture is going to be a rectangle. There we go. There's our picture. Now let's write some stuff down that we know about that picture. That's going to be step 3, where we assign the variables. In a rectangle, we know that we have a length and a width. I don't like using L and W because the L always comes out looking like a 1. So I'm just going to use the variables X and Y. All right? Now I'm going to try to put together all of this stuff that I have up here, all the highlighted stuff that I have. So let's see. This is where I'm writing my equations, by the way. One equation that I have is my area is going to be equal to, well, I have my area, it's 16 square inches. And I happen to know that in a rectangle, area is length times width. In this case, I have X times Y. Other equation that I have is the perimeter, because I want to optimize my perimeter. So my perimeter in a rectangle, again, this comes from geometry. You've done it before. Perimeter is just sum up all the sides. You could do X plus Y plus X plus Y, but really the easiest way to talk about that is 2X plus 2Y. Okay? So there's step, we're up to step 4. We've written our equation. Now, step 5 is going to be get the equation down to one variable. Again, we're trying to optimize perimeter. So this step where I get the equation down to one variable means make this side of the equation have either X or Y. In order to do that, I go back up to my other equation where I have 16 is equal to XY. And I just take one of those variables and I solve for it. It's whichever one I think is prettier. I think Y is prettier. I don't know why. So I'm going to divide both sides by X, which means I have 16 over X is equal to Y. I can now take this value and I can plug it in for Y right over here. So this equation now becomes 2X plus 2 times 16 over X. That's my perimeter. So now I've done step 5 where it is get the equation down to one variable. Now I am going to do the actual calculus. To do the actual calculus, I am just going to try to take my perimeter equation and find the, what did I want? I want the smallest, so I'm trying to find the minimum value for my perimeter and write down the dimensions of this rectangle. So in order to find the minimum, well, I have to differentiate this function. In order to differentiate this function, I would prefer to look at this as 2x plus 2 times 16 would give me 32. And we know from last chapter, taking the derivative of over x, we rewrite it as x to the negative first. So now I am going to find p prime. P prime is going to allow me to find my critical points of my perimeter. Critical points of my perimeter are going to be either my min or my max once I start to do some analysis and figure out which one it is. So P prime is going to be equal to, looking over here, first part, derivative of 2x, that's just going to be 2. Derivative of 32x to the negative first, well, I'd bring down that negative 1 times 32 becomes minus 32. X to the negative 1 minus 1 gives me 32x to the negative second here. So now I've got p prime is equal to 2 minus 32x to the negative second. And again, my whole goal here, to find my critical points, I want to take p prime. I'm going to put this in a separate step. I'm now trying to find my critical points. My critical points are going to be where p prime 2 minus 32. Now let's put the x squared down at the bottom. Is equal to 0. Now I just have to solve for x squared. I'll toss that 32 over x squared to the other side by adding it. 32 over x squared, add 32 over x squared. We now have 2 is equal to 32 over x squared. I'm going to run out of space, so I'm going to have to jump up here for some more room. But before I do that, I want to get x squared out of the denominator, so I'm going to multiply by x squared over here. Since I did x squared multiplied on one side, I got to do it on both sides to maintain my equality. So segmenting this off so I have some more space for my writing. Let's see. 2 times x squared is going to be 2x squared is equal to 30 dose. All right. Now again, I'm trying to get x by itself, so I'm going to divide by 2. I now have x squared is equal to 16. Taking the square root of both sides, remember since we introduced a square root, we have to say x is equal to plus or minus 4. So now we can say our minimum perimeter is going to exist when one of the side lengths is either 4 or negative 4. One of those answers doesn't make sense. You can't have a negative length. So our critical point is only the positive 4. We're ignoring the negative 4 because it doesn't make sense in this context. Now I do have to make sure that negative 4 is our minimum, because again, I'm trying to find the smallest perimeter. In order to make sure that it is the minimum, again, I use my sign chart to make sure it is the minimum. P prime, putting down positive 4 over here. If I plug in some number to the left of 4, like let's say 0, 2 minus 30, oh, I couldn't plug in 0. Maybe plug in 1. So 2 minus 32, 1 to the negative second power. That would be like 2 minus 32, which is going to give me a negative right there. If I plug in some number bigger than 4, like let's say 10 to the negative second is going to be 1/100th. 32 times 1/100th is 32 hundredths. 10 minus 32 hundredths. Okay, that's positive. Again, you can use your calculator to evaluate those if you want. But now what I see coming into 4, I've got a negative slope. Coming out of 4, I've got a positive slope. All of a sudden, I can see that, yes, indeed, that is a minimum. Minimum perimeter. Well, I guess it would be helpful to know what the perimeter is at that point, wouldn't it? So my minimum perimeter would be P is equal to, well, let's see, I've got a perimeter equation somewhere up here. Ooh, look at that. 2 times x plus 2 times 16 over x. So that's going to be 2 times 4 plus 2 times 16 over 4. Well, 16 over 4, that's 4. 2 times 4 plus 2 times 4, 8 plus 8. Ooh. My minimum perimeter is going to be 16. So if I have a rectangle with an area of 16 square inches, the smallest perimeter that I can make is going to be 16 square inches. And I can only go up from there. the dimensions of this rectangle? Well, one of the dimensions is going to be that x equals 4 by, now I just have to find out the other dimension, and the easiest way to find the other dimension, right up here. 16 divided by x gives me my other dimension. 16 divided by 4 gives me 4. 4 by 4. So it seems like the smallest perimeter is a square. All right, so I've run into difficulties from people in doing this type of problem before. So I'm trying to make a representation on a piece of cardstock here to show you exactly how this box is going to work. But let's read it first and see if we can understand it. So a rectangular piece of sheet metal is to have squares cut from the corners and have the sides folded up to make an open top box. Find the dimensions of the resulting box, which has the maximum possible volume if the sheet metal measures 10 inches by 20 inches. So first off, I'm going to point out that the cardstock that I have is not 10 inches by 20 inches. It's just a standard sheet of cardstock that I can get out of the get off of a printer or something. So what you can actually see on the cardstock that I have right here, I hope it comes through in the, there it goes on my doc cam. You can see I've marked off the corners here, and each of those corners is going to be a square cut off there. I don't know how much I'm cutting off, that's what I'm trying to determine. So seeing right here, I just cut that right out of there. From the magic of computer movie magic, I'm gonna show you what this box becomes. All right, so speaking of that movie magic, now I'm able to just cut off these corners. They come right away. See right there? So now what I have these tabs on each side that I'm gonna be able to fold up. So let me show you how that works. And now, from the magic of computers, I can now see that these tabs can fold up right here. And this is the open top box that I'm talking about. This, if I was able to fasten these sides together, this would be a box that has an open top with those tabs folded up. All right? So now, let's go back over to, not me, we want to see this. So we're going back over to the picture. So you can see in this picture, I have the squares cut out of the corners, and then I have over here is the actual picture of the box in 3D format. All right? So let's start understanding this question so that we can start to tackle it. It's a rectangular piece of sheet metal. Cut squares. Squares cut from the corners. Have the sides folded up to make an open top box. That's probably important. No, it's an open top box. Find the dimensions of the resulting box, which has the maximum possible volume if the sheet measures 10 inches by 20 inches. So now we can draw and label this picture. If I'm drawing and labeling this picture, well, I know that this whole side right here, how wide is it? 20 inches. And the height right there is going to be 10 inches. Let's label some other stuff. Oh, we don't know how much is cut out of the corner, right? So cutting out of the corner, we're just going to call that x. And since we're cutting squares out of the corners, all of these dimensions of these little gray parts right here are going to be x's, right? All right, so I think I've labeled my picture as much as I can. Well, actually, you know what? Since this whole distance is 20, I could probably find out this distance right here, couldn't I? That would be the full distance minus 2x. So just like from here to here would be 20 minus 2x. And same thing down here. This distance from here to here would be 10 minus 2x. How does that help me? How does that help me? Well, let's look down here on the picture. So again, just to give us some visualization here, this is that first picture that I had. Unfolded. Now when I fold up, I'm going to have the height of my box now. Notice the height of my box is the same as that cutout. And the width of my box is going to be the width of one of those tabs. The height of my box is going to be the height of one of those tabs. So let's go back over here and just transfer all those data points from up here down to here. I can now see that this is going to be 20 minus 2x. This section right here is going to be 10 minus 2x. And then the height of the box, that's just going to be that tab, and it's going to be that x right there. All right, so why does that help me out at all? Oh, let's assign some variables. Oh, I already assigned variables to the x. There's some other stuff that I need. Writing equations. So I know that I want to optimize the maximum possible volume. So I need to talk about the volume of the box. And the volume of a rectangular prism like this box is just going to be length times width times height. If only I knew what the length and the width of the height of the box were. Oh, wait a second. The length, width, and the height of the box were 10 minus 2x, 20 minus 2x, and x. Awesome. So now I have written an equation, and let's just check this equation. I went from 3 variables down to 1 variable, just x. Now all I need to do is find the min or max. Now I just need to do calculus. Now I would caution you, doing the calculus on this equation, finding the derivative of this is going to be awful because we have 3 factors, so we would have to do product rule 3 times, with the extended product rule with 3 factors. So instead, I'm going to use that old trick that I had from last chapter where I can just FOIL this out, make it into one polynomial so it's easier to find the derivative. So here I have first 10 times 20 will be 200. Outside, 10 times 2x would be minus 20x. Inside, negative 2x times 20 would be minus 40x. And last would be plus 4x squared. And it's still multiplied by x. Now I could do product rule on this one if I wanted to, but it's going to be much easier if I just distribute that x in. So now I can get my volume equation. It's going to be 200x minus 20 and 40 would be 60. X with another x would be minus 60x squared. Plus 4x squared times x, just 4x cubed. All right, cool, awesome. Now in order to maximize this possible volume, I need to look at my v prime. So my v prime is going to be derivative of this Joni McJonah right here, which is going to be 200x differentiates to, oh, that's linear, so that differentiates to 200, minus power rule over here, bring the 2 down, we get 120x plus 12x to the squared. Now we need to set this equal to 0. We need to solve this equation. We've got a couple of options for this. We could factor. Okay, no, I don't feel like trying to factor this. We could use the quadratic formula. I know all of us that had Mrs. Nicolia are now singing the x equals negative b plus or minus square root of b squared minus 4ac divided by 2a. Yeah. No, nobody's really doing that. We trashed the quadratic formula right after we learned it. So probably the easiest way to do this is to just kind of cheat. Again, this is not really cheating, it's just using our technology to make it a little bit easier. So what I'm going to do here, I'm going to put v prime into my y equals menu. So going into y equals, I said? Oh, helps out if I have my calculator accessible on my computer as well as on what you guys are looking at. Y equals, there we go, that's it. I want to plug in 200 minus 120x plus 12x squared. Now I need to look at what my possible cuts are on this on this figure. And in order to figure out my possible cuts on this, I'm going to look at this tangible example that I have right in front of me. So looking at, not me again, I want to get the sphere up here. So I'm looking here. If I'm cutting in from either side, there's a minimum cut that I can make. I know that I have to make at least a cut that is 0. So the smallest cut that I can make is 0, exclusive of 0. Now when I cut in, I'm going to be cutting in from both sides. So the furthest in that I can cut is actually going to be halfway into one of the sides. So if I cut in halfway from both directions, I'm going to cut off that entire tab. So what I look at here, back onto this example, I look at the shortest side right here. The shortest side is that 10 inches. So it looks like the most that I can cut in is going to be 5 inches. So this is just helping me identify the domain of X. Domain of X is going to be between 0 and 5. Why do I do that? It's because now when I look back at my calculator, I know that what I graph is only going to be between 0 and 5 because my possible cut is somewhere in between there. Now when I go and graph it, I'm going to be able to see that right, where's my mouse? Right here is the 0 that I'm concerned with. To find that 0, go to second calc, 0, left bound. I just want to make sure that it's to the left of that point. There we go. I'm actually keeping my eye on my y values right here to see when it's to the left, because I know that when I'm to the left of x, this y value has to be positive. And when it's to the right, it has to be negative. I'm just reading the graph to see that. Then guess, it looks like 2.113. 2.113. 2.113 is my answer. So x is approximately 2.113, and 2.113 inches would be appropriate. Now we do have to verify that that is the maximum. It's really easy for us to verify that this is the maximum because we are just looking at our v prime. If we look at our v prime, we actually have this set up in such a way that it's easy to interpret. Let me get my calculator accessible here, because I can see to the left of this 0, my v prime is actually positive. To the right of the 0, the v prime is negative. Because I have v prime graphed right here, I can just see the relative locations of where the graph is. So again, I'm using my technology to make life easier. Move that a little bit so that you can see I'm talking about my critical point of 2.113. To the left of 2.113, v prime is positive. To the right, it is negative. So it looks like I do indeed have a maximum. So now I actually have to figure out what the volume is and what the all the length, width, and height. So the dimensions, I'm again going to cheap out a little bit and use my calculator to get these dimensions. Since the last thing that I did on my calculator actually had me determine the x value without hitting left or right, if I quit out of this menu, anytime I hit x, I now have x stored as 2.113. So now I can just figure out my the length, width, and height are just these quantities that I've already set up. That 10 minus 2x, the 20 minus 2x, and the 2x are my 3 dimensions of this box. So looking on my home screen, 10 minus 2x, 20 minus 2x. And to find the volume is just going to be that 200x minus 60x squared plus 4x cubed. So now I'm able to read that directly off my screen. So now I can see the dimensions of my box are going to be, just reading them, 2.113 inches by 5.774 inches. 5.774 inches by 15.774. 15.774 inches. And the volume, the maximum volume I can make out of this, is going to be 192.450. 192.450 cubic inches. There we go. Fun times. And I got one other type of problem. And it's this one. A rectangle is to be inscribed in the semicircle whose equation is x squared plus y squared equals 16, so that the upper vertices of the rectangle are on the semicircle and the lower vertices are on the x-axis. Let's spread this out so that I can actually get some more space to write and draw stuff. All right. Okay, that sounds really weird. Let me see if I can draw that, because here I'm trying to read and understand it, and reading and understanding it just isn't making sense to me. So just a couple things. I've got, this is probably important. X squared plus y squared is equal to 16. That's going to come into play, I think. Upper vertices of the rectangle are on the semicircle. Upper vertices on the semicircle. Lower vertices on the x-axis. Find the dimensions of such a rectangle with the maximum area. So those are the important things. Again, I don't quite understand what's going on here, but let's see if drawing my picture is going to work out here. So I know that I'm going to have a rectangle. The rectangle is going to have the upper vertices on the circle. They should be reflected over the y-axis, and the lower vertices are going to be on the x-axis. So there I have my rectangle, right? Well, actually, I have some numbers that I can assign here, because this point right out here is just going to be called xy, and that point is going to be on the semicircle that's described right here. Well, I know that this value right here, from here to here, is going to be x, and this value from here to here is going to be y. Why does that help me? Because the area of a rectangle, which I'm trying to maximize, is going to be equal to length times width. Well, here, I'm just going to try to find out the width of this entire rectangle. Well, if this part is x, well, then that part's x too, and we have x and x gives me 2x is the width of my rectangle. So now I can find out that the area of my rectangle is going to be 2x times y. Okay, so now I have drawn and labeled the picture. I have assigned variables. I've written my equation. The only thing left before I do calculus is to get this variable down to one, or to get this equation down to one variable. And to get this equation down to one variable, I need to use this guy right here, where I have x squared plus y squared is equal to 16. Solve that for one of the variables. Again, I just think y is prettier, so I'm going to solve it for y. Subtracting x squared from both sides, I know I've got y squared is equal to 16 minus x squared. Going a little bit further, I now know that I've got, taking the square root from both sides, I'm going to have y is equal to the square root of 16 minus x squared. I'm not going to do the plus or minus because I only have the positive circle that I'm dealing with here. All right? So now I can go back in here and I can figure out that this is going to be 2x times the square root of 16 minus x squared. I am now going to have to find a prime set a prime to either 0 or undefined. Before I try to find a prime, I'm going to show you guys a little trick in order to make this a little bit easier. Because this, I'm going to have to use product rule on this one. I don't feel like using product rule, and there is a way around me using product rule. This may have popped up in class before, it may not have, but this is a nice way in this particular circumstance to not use product rule. I know that x is the same thing as the square root of x squared. I squared it and unsquared it at the same time. Still keeping square root of 16 minus x squared over here. Now I have that x squared underneath the radical. I can now distribute that x squared into the 16 and the minus x squared. I now have my area in one variable is going to be 2 times the square root of 16x squared minus x to the 4th. Adding the variables on x squared and x squared when I multiply them together. Sweet. That makes it so much easier to deal with because now a prime, I'm going to have that 2. And now I just have to take the derivative of a square root. And we know from last chapter, the derivative of the square root is 1 over 2 times the square root of the stuff. But now, since I have stuff inside of there, I need to multiply by the derivative of the stuff. So the derivative of the stuff would be 16x squared becomes 32x minus derivative of x to the 4th, 4x cubed. Just double checking my work. All right, cool. Now I'm going to simplify this a little bit. 2's go bye-bye. I now have 32x minus 4x cubed over the square root of 16x squared minus x to the 4th. Simplifying this a little bit, I can factor out the x squared in the denominator. I've got 32x minus 4x cubed over the square root of x squared times the square root of 16 minus x squared. That becomes just x. So now, if I factor out an x in the numerator, I've got x times the quantity of 32 minus 4x squared over x square root of 16 minus x squared. Almost there, almost there. Whew. We now get this is 32 minus 4x squared over square root of 16 minus x squared. Sweet. So now all I have to do is find out what makes this 0, what makes this undefined. So making this 0, making this undefined. Let's see here. Make it 0 is going to be where 32 minus 4x squared equals 0. Subtracting 32, I got negative 4x squared is equal to negative 32. Divide by negative 4, I got x squared is equal to 8. Take the square root, I've got x is equal to the square root of 8, or 2 root 2. There's one of my solutions. Again, I'm neglecting the negatives because, well, this is a real tangible problem. I can't have negative square root of 8 as a dimension. Making this undefined is where the square root of 16 minus x squared is going to be equal to 0. Square both sides. We've got negative x squared, or sorry, 16 minus x squared is equal to 0. Subtract 16. We've got negative x squared equals negative 16. Divide by negative 1. We got x squared is equal to 16, or x equals 4. If I made this into x equals 4, I'm going to point out right over here that my y value would actually be 0. So this one is not going to be a candidate for my maximum. Now, all I have to do, I'm going to say that my maximum is going to be produced by 2 root 2. I need to go down here and make my A prime sign chart. So I got A prime right here. I put 2 root 2 on there. To the left of 2 root 2, let's say, for example, I don't know, 0 left of 2 root 2. I can plug 0 into my A prime. I would have 32 minus 0, so 32 over the square root of 16. So it looks like that would be positive. To the right of 2 root 2 would be something like 3. I could have 32 minus 4 times 3 squared. 3 squared is 9. 4 times 9 is 36. 32 minus 36 is going to give me that negative. Since I got the square root, that's going to be positive down there. So negative divided by positive gives me negative. I can now analyze that a little bit further. Up and then down, it does look like I have a maximum at 2 root 2. Max. Where x equals 2 root 2. Therefore, y is going to equal, let's see if I find my, oh, there it is. It's right here. It's right here. Y expression would be the square root of 16 minus 2 root 2 squared, also known as just the square root of 2 root 2 squared would be 8. 16 minus 8 gives me 8. Oh, hey, look at that. 2 root 2 for my other dimension. So it looks like the maximal area is going to be where the x value is 2 root 2, y value is 2 root 2, which means the dimensions of this rectangle. Remember, the 2 dimensions that we had were 2x and y. So the dimensions of this rectangle are going to be 2x, or 4 root 2, by y, 2 root 2. Area is just going to be length times width, so 4 root 2 times 2 root 2, 8 times 2, which would give me 16 square units. Whew, fun times, fun times. And that's the end of that. Advance. My computer's given up on thinking here. And come on. There's some practice problems. Try to look at those. We'll do some of them in class tomorrow, and I will see you then.